In geometry, a circle is one of the most fundamental shapes we encounter, but what exactly defines a circle? We begin with a single fixed point in space. This point will serve as the center of our circle, the anchoring point from which all measurements will be taken. What makes a circle special is that every point on its boundary has exactly the same distance from this center point. This constant distance is what we call the radius. Let's place several points around our center, each exactly the same distance away. These points will lie on what will become our circle's circumference. To visualize the equal distances, let's draw lines from the center to each of these points. These lines represent the radii of our emerging circle. The red markers highlight that each radius has identical length. No matter which direction we move from the center, as long as we travel exactly this fixed distance, we'll reach a point on the circle. If we were to plot every possible point that sits exactly this fixed distance from the center, we'd trace out a perfect circle. The smooth curve emerges naturally from this distance constraint. These radial lines demonstrate the key structural property of circles, the constant radius. Each line connects the center to the circumference along a different path, yet all have exactly the same length. This constant distance, which we denote with the letter r for radius, is the defining parameter of any circle. It completely determines the circle's size. From this geometric understanding, we can derive the formal mathematical definition of a circle. This elegant definition, the collection of all points at the same distance from a center, is what gives rise to the circle equations we use in coordinate geometry. The standard and general forms of circle equations are simply algebraic expressions of this fundamental property. The key takeaway is that a circle is defined by its constant radius property. Every point on the circle is exactly the same distance from the center, no more, no less. Let's explore how the equation of a circle is derived from the distance formula. The distance formula is fundamental to understanding why a circle's equation takes the form it does. Here's a circle with center at the point 3, 2 and radius 2. Notice how every point on this circle is exactly 2 units away from the center. The center of any circle can be represented by the coordinates h and k. These variables are commonly used in the general form of a circle's equation. In our specific example, the center coordinates are h equals 3 and k equals 2. These values will be substituted into our final equation. The radius of a circle is the constant distance from the center to any point on the circle's circumference. This fixed distance is what defines a circle geometrically. For our circle, the radius is 2 units. Remember that the radius is critical for a circle's equation because it determines the size of the circle. Now, let's consider any arbitrary point on the circle and call its coordinates x and y. These variables will represent all possible points that lie on our circle. Here's the key insight. For any point on the circle, the distance from that point to the center must always equal the radius. This constant distance property is what we'll express mathematically. Using the distance formula, we can write that the square root of the quantity x minus h squared plus y minus k squared equals r. This formula calculates the distance between the center point h, k, and any point x, y on the circle. To eliminate the square root, we square both sides of the equation. This gives us x minus h squared plus y minus k squared equals r squared. This cleaner form is known as the standard form equation of a circle. Substituting our specific values, we get x minus 3 squared plus y minus 2 squared equals 4. Notice that 4 is the square of our radius, which is 2. This equation precisely defines our circle in the coordinate plane. This equation elegantly captures the fundamental property of a circle, that every point on the circumference is exactly distance r from the center. Any point whose coordinates satisfy this equation must lie exactly on our circle. Conversely, every point on our circle must satisfy this equation. This mathematical relationship between geometry and algebra allows us to precisely define shapes using equations. The standard form equation x minus h squared plus y minus k squared equals r squared works for any circle, regardless of its center or size. This makes it extremely powerful for analyzing and working with circles. This equation forms the foundation for solving many geometric problems involving circles. It allows us to find intersections with other shapes, determine whether points lie inside or outside a circle, and even derive equations of tangent lines. The equation x minus h squared plus y minus k squared equals r squared is the standard form of a circle's equation, where h and k represent the center coordinates, and r is the radius. This elegant formula directly connects the geometric definition of a circle with its algebraic representation. Let's explore how the standard form of a circle equation relates to its graph. The standard form equation allows us to precisely define a circle's position and size on the coordinate plane. The standard form of a circle equation is written as open parentheses x minus h close parentheses squared plus open parentheses y minus k close parentheses squared equals r squared. In this equation, the point hk represents the center of the circle and r represents the radius. Right now, our circle is centered at the origin with coordinates 0, 0 and has a radius of 2. When the center is at the origin, we can simplify our equation to x squared plus y squared equals 4. This is because subtracting 0 doesn't change the value, and 2 squared equals 4. This simplified form is often used for circles centered at the origin. Now let's see what happens when we change the h value in our equation. The h parameter controls the x-coordinate of the center. When h is positive, the circle moves to the right, and when h is negative, the circle moves to the left. As you can see, when h increases from 0 to 3, the circle shifts horizontally to the right. This demonstrates how the h parameter directly controls the x-coordinate of the center. Note that the equation changes from x squared plus y squared equals 4 to open parentheses x minus 3 close parentheses squared plus y squared equals 4, reflecting this rightward shift of 3 units. Next, let's examine how the k parameter affects the position of the circle. The k value controls the y-coordinate of the center point. In our equation, the k parameter appears in the y term as open parenthesis y minus k close parenthesis squared. When k is positive, the circle moves upward, and when k is negative, the circle moves downward. Let's observe this effect by gradually increasing k from 0 to 2. Just as we expected, as k increases from 0 to 2, the circle moves upward along the y-axis. The equation changes to x squared plus open parentheses y minus 2 close parentheses squared equals 4. This vertical shift is reflected in the new center coordinates of the circle, which are now at point 0, 2. Finally, let's investigate how the radius parameter r affects the appearance of the circle. Unlike h and k, which determine position, r controls the size of the circle. The radius r appears in our equation as r squared on the right side. This value determines how far the circle extends from its center. A larger value of r creates a bigger circle. Let's watch what happens as we increase r from 1 to 3. As r increases, the circle expands outward in all directions. Notice how the equation changes from x squared plus y squared equals 1 to x squared plus y squared equals 9 when r equals 3. The squared term on the right side grows quadratically as the radius increases, which makes sense geometrically since the area of a circle is proportional to the square of its radius. Now that we understand how each parameter works individually, let's combine all 3 parameters to see how they interact to define a complete circle. We're starting with our original circle centered at the origin with radius 2. Now let's change all 3 parameters simultaneously to create a different circle. We'll set h to 2, moving the circle to the right, k to 1, moving the circle upward, and r to 1.5, adjusting the size. We've now transformed our circle to be centered at the point 2, 1, with a radius of 1.5. The equation reflects all these changes. Open parentheses x minus 2, close parentheses squared, plus open parentheses y minus 1, close parentheses squared equals 1.5 squared. This demonstrates how the 3 parameters work together to completely define any circle on the coordinate plane. The standard form of the circle equation provides a powerful and concise way to describe any circle. By adjusting the parameters h, k, and r, we can precisely control both the position and size of a circle. This makes it much easier to work with circles in coordinate geometry. The standard form of a circle equation connects algebraic expressions to geometric properties. When you see the equation open parentheses x minus h close parentheses squared plus open parentheses y minus k close parentheses squared equals r squared, you can immediately visualize a circle with center at h, k, and radius r. This connection between algebra and geometry is one of the fundamental principles in coordinate geometry. Let's explore how the standard form of a circle equation can be transformed into the general form through algebraic manipulation. In the standard form of a circle equation, the values h and k represent the x and y coordinates of the center point, while r represents the radius. This creates a set of all points that are exactly r units away from the center. To transform this equation, we'll first expand the term x minus h squared using the binomial formula. This gives us x squared minus 2 times h times x plus h squared. We'll do the same expansion for y minus k squared, which follows the same pattern. This gives us y squared minus 2 times k times y plus k squared. Now that we've expanded both squared terms, we can substitute these expressions back into our original equation. This will allow us to rewrite the standard form in terms of the individual variables. Let's simplify by removing the parentheses. Since we're just adding the terms together, we can write them all in sequence. To arrive at the general form, we'll rearrange the equation so that all terms are on the left side, with 0 on the right. We do this by subtracting r squared from both sides of the equation. Looking at our equation, we can identify patterns that will help us simplify it further. Let's introduce 3 substitutions. First, we'll replace negative 2h with the coefficient d, which is the coefficient of the x term. Similarly, we'll replace negative 2k with the coefficient e, which is the coefficient of the y term. Finally, we'll group the remaining constant terms, h squared plus k squared minus r squared, and call this f. Notice that f contains information about both the center coordinates and the radius. With these substitutions, we can now rewrite our equation in the general form. The x squared and y squared terms remain unchanged, while the other terms are replaced with our new variables d, e, and f. This general form, x squared plus y squared plus dx plus ey plus f equals 0, gives us the same circle as the standard form. The coefficients d, e, and f encode all the information about the circle's position and size. If we know the values of d, e, and f, we convert back to the standard form by determining h, k, and r. For instance, h equals negative d divided by 2, k equals negative e divided by 2, and r can be calculated from f once we know h and k. We've now fully transformed the standard form of a circle equation into its general form. While the standard form makes the center and radius explicit, the general form is often more useful in analytical geometry and when solving systems of equations. Let's explore the relationship between the standard and general forms of circle equations, 2 key ways to represent circles mathematically. The standard form of a circle equation shows us the center and radius explicitly. Here, h and k represent the center coordinates at the point h, k, while r represents the radius of the circle. The general form looks quite different with coefficients d, e, and f. This form is often what we encounter after algebraic manipulations, but it doesn't immediately reveal the circle's properties like the standard form does. To convert between these forms, we need to understand the relationships between their coefficients. These relationships are derived by expanding the standard form and collecting like terms. The first relationship tells us that d equals negative 2 times h. This comes from expanding the x minus h squared term in the standard form, which gives us x squared minus 2h times x plus h squared. Similarly, the second relationship shows that e equals negative 2 times k. This relationship emerges when we expand the y minus k squared term, which gives us y squared minus 2k times y plus k squared. The third relationship is that f equals h squared plus k squared minus r squared. This comes from combining the constant terms after expansion. The h squared and k squared terms come from expanding the squared binomials, while the r squared term moves to the other side of the equation. These relationships are powerful tools that allow us to extract the center coordinates and radius from a circle equation given in general form. Let's work through an example to see how this works in practice. Consider this circle equation in general form: x squared plus y squared plus 4x minus 6y plus 12 equals 0. Our goal is to rewrite this in standard form to identify the circle's center and radius. The first step is to identify the coefficients by comparing with the general form. Looking at our equation, we can see that d equals 4, e equals negative 6, and f equals 12. Now we can use our first relationship, d equals negative 2h, to find the x-coordinate of the center. We have 4 equals negative 2h, so solving for h, we get h equals negative 2. This means the center's x-coordinate is negative 2. Next, we use our second relationship, e equals negative 2k, to find the y-coordinate. We have negative 6 equals negative 2k, so dividing both sides by negative 2, we get k equals 3. This means the center's y-coordinate is 3. Finally, to find the radius, we use our third relationship, f equals h squared plus k squared minus r squared. Substituting our values, we get 12 equals negative 2 squared plus 3 squared minus r squared. Simplifying the right side, we get 12 equals 4 plus 9 minus r squared, or 12 equals 13 minus r squared. Rearranging to solve for r squared, we get r squared equals 13 minus 12, which is 1. Taking the square root, we find that r equals 1, which is our circle's radius. Now we can write our circle equation in standard form. Since h is negative 2 and k is 3, we have x minus negative 2 squared plus y minus 3 squared equals 1 squared. Simplifying our expression, we get x plus 2 squared plus y minus 3 squared equals 1. This standard form clearly shows that we have a circle centered at the point negative 2, 3 with a radius of 1 unit. By using the coefficient relationships we derived earlier, we've successfully converted a general form equation to standard form, revealing the geometric properties of our circle. This technique works for any circle equation in general form. Remember these key relationships when converting between forms. d equals negative 2h tells us the x-coordinate, e equals negative 2k gives us the y-coordinate, and f equals h squared plus k squared minus r squared lets us find the radius.